you know H, you know G, you should be able to determine R from here. This is non-linear equation to solve, but for large enough and you can start by approximating R to the n by 0. That will give you a value of R that may not be perfectly accurate, but then you can substitute back that value of R here to get the R to the n and repeat. And if you go on repeating this 3 or 4 times, even without any computer program or any nonlinear equation solver, you should be able to easily find out the value of R. So this is a decent enough experiment. Now I said sufficiently high number, but not too high a number. Now anybody who has dropped a marble on a floor, and I guess all of you have done that sometime or the other, would know why. Because after a while the bounces get so close together, distinct bounces or not. Is that okay? So when I drop maybe 10 bounces, I can still distinctly count. After 11 or 12, after 15 bounces, it sort of sounds like. So that would be very difficult to count. So you have to make a sort of judgment between getting a high enough number so that you are reasonably sure that your experimental errors are reduced, but not too high a number when you cannot distinguish one bounce from another. Well, this of course has several shortcomings. Human response time is the hugest shortcoming. That is, you have to hear the first bounce and immediately start the stopwatch. Then you have to stop the stopwatch immediately after you hear the 10th bounce, for example. But this time interval is usually pretty small, and human response time is actually quite a large fraction of that. So since you have 2 times where you have to start and stop the stopwatch, responding to the noise, it becomes quite inaccurate that way. Well, counting bounces, anybody who has done an experiment would know that counting things which occur over and over again is tedious and sometimes error prone. And more importantly, this may give you the value of R at the end, but it does not give you any way of verifying whether this R to the n law, that Tn is really R to the n times T0, T1, sorry, the first bounce, is that you cannot really check. Right? Because the individual bounces happen too close together for you to keep on measuring every one of them with your stopwatch. So the formula Tn is R to the n T1 is something you can derive from basic theory, but there is no way that you can check that experimentally. You have to take that as a given fact and then just use that to sort of verify whether this is really working out. And finally, I promised you that we will be able to determine G using this method, but what I have described so far, you have to use G as an input. You cannot really, because you need to put in G in this formula, this root over 8H by G. Factor has to be there. Then you have to multiply, then you have to use that to find R. So this can give you a sort of close approximate value for R, will not be very good or will not be very accurate, but it can be done. At least if you don't have any other equipment, this at least gives you some way of measuring the coefficient of restitution, which is not too bad. Okay, but now I'm going to describe how you could use software, a rather simple software to use, and simple equipment to try to improve on the accuracy and scope of this experiment by a long margin. So what do we do? Well, what we need for the more detailed or more precise experiment is the following. You still need steel ball bearings or glass spheres, marbles. You still need a hard surface. That much is common. The new thing is you no longer need a stopwatch, but what you do need is a laptop or a desktop or a mobile phone with a microphone. Anything with a microphone would do. Anything which can record sound. Mobile phone is fine. And I missed out on one thing. You do need a tape or some other method of measuring the height. Because you have to release the ball from a pre-measured height. Of course, if you already have something whose height you know, you can just use that as a reference. And then you need audio processing software. Some software which will allow you to see the audio waveform and measure things from that. Now the one which I used, and the one which I recommend that everybody uses, is called Audacity. Of course, the word name Audacity is a pun. It's audio processing software. That's why it's called Audacity. Audacity, of course, means something quite different in English. We will be using that. And then, the reason why, okay, let me just tell you why I like using Audacity. Among several reasons, one of them is Audacity is free. It used to be open source, which was another reason why I used to love it. But nowadays it's no longer fully open source. That's bad. But at least it's available completely for free. It's available not only for Linux, which is my favorite operating system. It's available for almost every operating system. The only drawback for using Audacity that I have found so far is that it's not available yet. At least a stable version is not available yet for the mobile phone. That is, at least for Android, Audacity has not yet come up with a stable port. That would have been wonderful. If you had an Android version of Audacity, you could actually do this experiment entirely with your mobile phone without using anything else. Okay. Right now, at least I actually recorded the sound using my mobile phone microphone and then had to transfer the file to my laptop for doing this Audacity processing. Laptop, desktop, anything will do. Any operating system that you can think of, Audacity has a port for it. And unfortunately, phone operating system. There is a version, but it is not really very good right now. There are other software available for mobile phones which can do this job, but not as well as or as nicely as Audacity. So I would recommend that you should use Audacity for this if you want to do this experiment. Of course, you can find your own favorite audio processing software, and if it allows you to see the waveform and measure times from there, that's all you really need. Now, there's another reason why I use Audacity, that's primarily for Audacity, after all, is really meant for audio editing. So, well, if you have music which you want to edit, or for the last couple of years, the lectures that we are uploading up online, I don't have a studio or a very nice, equipment for which I can get nice soundproof recordings. So my sound recordings have a lot of noise, lots of external, you have horns, honking, somebody shouting nearby, and all that goes into the recording. Now, using Audacity, you can get rid of those things as much as possible so that you can get a relatively clean recording to upload. So that's the reason why I use Audacity all the time. So I'm very familiar with that. But it's very easy to use, so you don't really have to be very familiar before you can start using it. Okay, the procedure is straightforward. You drop the ball bearing on the hard surface from a measured height, as before. But instead of trying to count the bounces and record and start and stop a stopwatch, you're not even using a stopwatch. You just record the sound. You just record the sound using your mobile phone. Or, in fact, if you have a laptop which you can move close to the source, you can just directly record the sound using the laptop mic. And then you have to either transfer the sound file to your laptop. That's pretty straightforward. Or if you're using the laptop to record, you don't need that step at all. You just open the sound file using the Audacity program. And if you open the sound file, let me just show you what you will see. This is from an experiment which I did. You get to see spikes like these. These are basically points in time. Okay, on this scale, you can see the time. Okay, so this entire experiment lasted for around 11 seconds. As you can, even less than 11 seconds. Sorry, what happened? Yeah, around The first bounce occurred at around 0.6 seconds, and around 11 seconds the bounces got too close together. So whereas by ear you can sort of count 10 or 12, here you can see clearly that in principle I can see clear bounces 1, 2, 3, 4, 5. Okay, roughly around 30 odd bounces you can easily. Very well. You don't have to use this screen. You can easily zoom in into the waveform, and if you zoom in hard enough, you can see this is where the bounce is occurring. Okay, and see on this scale you can measure off the time, and this shows that at least you can get near millisecond accuracy using this. The time at which a bounce occurs, you can time it to near millisecond accuracy. Okay? So, if not a millisecond, now, can you really get a millisecond? The answer is no, because the sound may not be that sharp. It may be difficult to figure out exactly when the sound starts. In that case, it may be a few milliseconds, not a fraction of a millisecond, as you can see in this case. Actually, this is 3.5690 seconds. This is 3.5695 seconds. So if I take this as the start of the bounce of this loud noise that happens the moment it bounces, you're going to see is 3.5694. Now going up to 4 decimal places, that is fraction 1/10 of a millisecond, that may be overdoing it, but you can definitely get millisecond accuracy, if not that, at least a few milliseconds accuracy, which is definitely far, far better than what you can ever do using a stopwatch, simply because your response time would be a lot worse than this. So this is how accurately you can measure off times. Now, one problem, of course, if you go back to this, you will see the first bounce occurs here, but that is some arbitrary time, because frankly it depends on when you started your recording, when you dropped it. You may not have dropped the ball immediately at the moment you start the recording, and it doesn't really matter, because what you will need are the time intervals, the time interval between the first and the second bounce, the second and the third bounce, third and the fourth bounce, and so on. So now, this is a result of an experiment that I carried out at home. The red dots here actually determine the time intervals between the bounces. So I first zoomed in. Now this is something which actually you could write a small program, say in Python, using the Python sound library. So those of you who know Python could try this out as a nice exercise. There is a library in Python, a module called PSL, the Python sound library, which allows you to import the waveform in and then do various things with the waveform directly. The waveform gets converted to a bunch of numbers, and then you could use the numbers directly. And you could automate the whole process. That is, you could write a program which would find out exactly when the sound rises above a threshold and note down those times, and then do all the rest of the calculation within the program itself. You could do that. That would be a nice programming exercise. It's also a bit of a bore, because after that, if you do that, then the experiment. Of course, there's this debate between how much automation is good and how much is bad. So I will leave each one of you your own, to decide on your own which one you would want to do. But at the very least, what you could do is simply note down the time intervals on a piece of paper. Either use a calculator or the computer itself, or simply do it in your head to find out the time intervals. And here, this is a plot which was done using a computer, of course. And this one, because I was using a computer software, basically GnuPlot, to plot and fit data, I fitted the best fitting curve Tn equal to AR to the n to this, and this fit, the blue line is a fit. So you could see that the blue line actually fits the red dots rather well. So this rule that we have, that the time interval varies in a geometric progression as the bounces increase. That's verified rather well here. This curve actually fits very, very well. And from GnuPlot, I could get the best fit values of this quantity A, which is the root over 8h by g in front, and the coefficient of restitution R, which came out to be 0.952. This is steel on glass, and the references I could find, coarse steel on glass as 0.95 to 0.98. 0.95 is a pretty decent value for R in that sense. And if you use the value of A, since A is root over 8h by g and we have measured h, you can actually use it to find the value of g. Now, if anybody has seen in fact, I had actually sent this over beforehand, these slides over beforehand, but there you would see the value quoted is 10.23 for g, 10.23 meters per second square. Only later I discovered that the height which I had taken to be 30 centimeters was actually, I did take a 30 centimeter long rod to measure the height, but the rod actually was bent. Thankfully, I had taken a picture of that, and so I could measure the angle from the picture, and I could estimate that the height actually was 28 centimeters, not 30. That was an experimental error. Of course, I had to do everything while holding the microphone, holding the camera, because I was also filming that. And that actually led to a bit of an error. But if you use 28 centimeters, you get 9.6 meter per second square. Even if you use 30, you get 10.2, which is actually not bad at all. Even 10.2 is around a 4% error, right? 9.8, 10.2, 0.4 out of 10. So nearly 4% error, which is definitely on par with whatever you do in your lab. In fact, usually it's better. And you can actually make this more precise. And if you had repeated it for different heights and so on, which takes hardly any time, right? Because to do the experiment takes a few seconds. You have the recording, then you can, at your leisure, put this in a computer. If you are using a program to measure of the times it takes and calculate the result, it takes microseconds to work the whole thing out after that. But even if you're reading off the times by zooming in yourself physically, it's still a decent, maybe half an hour or so is the maximum time you need for one complete experiment. So you can repeat it for 3 or 4 heights to get a better value. But what I'm trying to point out here is that in this case, all you used was very little equipment, the mobile phone for recording. And I'm assuming that you have an access. Okay, this is the difficult part. I have to assume that everybody has access to a working desktop or a laptop, which is not too bad an assumption nowadays. But of course, you may not have a desktop or a laptop at home. You can then use your mobile phone to do the same kind of thing. But on a mobile phone, I have not really been able to find a very good waveform measurement system. There are a few, in fact. So if anybody finds one, I would be very happy to know. Anybody finds one where it's easy to actually, I found several, but there is slightly more difficult simply because it's difficult to handle the small screen with your fingers and so on. So I'm not very happy with the mobile phone versions as of now. If somebody finds a better, at least an adequate software for that, it would be very nice. Then you could just use the mobile phone and that's it. Okay, at this stage, okay, are there any questions? And I have to sort of know whether I'm still connected. Yeah, I am.
Yes.
Please.
Yes, you are connected. The audience, please, if you have any question, please ask to the speaker directly.
If not, I'm nearly at the end of my talk, actually.
No.
I had a long slot given to me, but frankly, I don't have all that much to say. Okay, it's not at the end, but close to the end, anyway.
We can request participants to write their questions in the chat box. And maybe we can take them in the end.
Okay, we can take them at the end if there are questions.
Yeah. So
I actually asked this more to figure out whether I'm still connected or not. Anything else?
Yes, sir.
Okay, so let's go back. Okay, now if you are not using software to plot and fit the data, it's still okay. In fact, it's actually nicer, perhaps because it also tells you how to handle this kind of data. Since the best thing to do if you are using graph paper at home is to try to plot a straight line graph. That's what we have been always taught, because if you manage to send a curve through a bunch of points, you may not be able to tell from the curve whether it's actually whether it really obeys the formula that you predict it obeys. But a straight line is easy to see using the naked eye. So since your prediction is Tn is AR to the n, the obvious thing to do would be to plot log of Tn versus n, the number of bounces. And if you do that, you should get a straight line. So this would be a very easy way to check using graph paper whether this Tn equal to AR to the n is right. All you do is plot log Tn versus n. And then of course the intercept would be log A and the slope would be log R. So you have a bunch of points which should fall pretty closely on a straight line. Then you should draw a best fit straight line to this graph, which I'm pretty sure every student in the audience knows how to do. And from the intercept and the slope, find out log A and log R. That of course gives you R directly by exponentiating. And once you've got log A, you find out A, you use A equal to root over 8h by G. Since you have measured H, you can find G from there. And I will just finish talking about this particular experiment by essentially saying that if you wanted to find out the standard classical methods for finding out E, the coefficient, okay, I'm sorry about this change of notation. This E is what most people use for coefficient of restitution. E is connected to elasticity, so that's why they use E. So this E is not the base of natural logarithms. This E is what we have been calling R. I should have actually changed this. Anyway, there are several methods. One is the measurement of vertical rebound, which simply means you drop the thing on the ground, try to find out how high it rises. Not a very accurate thing to do, simply because you have to drop the thing completely vertically, number one, and number two, you have to be very careful in finding the exact height. Well, actually, even that could be improved using today's techniques simply by, say, using a mobile phone to record a video for this, and then use a software like Tracker, which I'm pretty sure many of you have already heard about, and using which you can find out exactly what height the thing reached. That is, you can see the pictures frame by frame and then figure out the maximum height. That would be pretty nice. The next method that is talked about is spark photography, which is basically taking very fast photographs at very small time intervals. Nowadays, of course, we have high-speed movie cameras, and you could also use trackers. You could use high-speed movie cameras. The trouble is, when you drop a ball directly on the ground, the thing takes too little time to actually accurately measure the height using a mobile phone camera. It would be better if you used a faster camera. The trouble with mobile phones is really not in the speed of the shutter. It's more in the fact that the sensors that are used in mobile phone videos are not really that fast. So your dropping ball would look more like a blur here. Now, another method which is actually better in the sense that is easier to do experiments with involves the inclined plane. That is, you want to find out the angle at which a dropped ball would rebound from the inclined plane. If it were perfectly elastic, of course, then the rebound would essentially obey the same law as reflection of light. That is, equal angles on the incident and the reflected side. But because of the fact that some of the energy is lost, that will not happen. By measuring the angle at which it rebounds, you can actually again measure the coefficient of elasticity. And then there's something called the double ballistic pendulum method of Thomas, which essentially means you have a pendulum, stationary pendulum on which you hit on which you try to sort of project the object very fast. It goes and hits it, makes it bounce. And then it hits another pendulum and that makes it stop. And it's a pretty complicated method, but that's supposedly the most accurate method available. Now, all of these methods actually are either difficult to perform accurately or are often very expensive. The double ballistic pendulum method is very expensive. If you want to use a high-speed movie camera, that of course would cost a lot of money. On the other hand, all we needed here was, of course, we needed a laptop or a desktop, but that was more like an instrument to be used. But the real thing that you needed for the experiment were steel balls, a hard floor, and a microphone recording system, maybe even your mobile phone. So this method is quite cheap and frankly, it's quite accurate. And if you do it with care, I am reasonably sure, because I have done this experiment several times, that at least the measurement of G is usually way more accurate than what you can achieve in a standard undergraduate physics lab, with almost no investment whatsoever. Now, finally, I will talk about one more thing, which frankly I don't think I need to talk about, because I have already seen that Ranjit, for example, my colleague Ranjit Bhattacharya, has already talked about Firefox or Firefox. That's what the Germans who started this thing actually calls it. So I'm not going to spend a lot of. I actually wanted to talk a bit about Firefox experiments, but then I saw that Ranjit has already done that. So just in case some of you missed Ranjit's lecture, let me just quickly tell you that Firefox is it's not really an Android app. It's available as an Android app, but it's also available for Arduino. It's also available for Mac iOS. But for us, the most important thing is it's available for your mobile phone as an Android app, which essentially converts your mobile into a lab. And you can do all kinds of experiments with it. It can be downloaded and used for free. In fact, you can contribute to the further progress of this. You can try to design your own experiments using Firefox, and you can contribute that. And that will be, as long as it's okay, it's going to be accepted, and you will have a permanent place in some application for your own work. Now, this was developed by Professor Heidrun Heinke, Sebastian Starks, and Christopher Stamper, and in fact, quite a few others. And these three, I'm specially naming them because they were awarded the Ars Legendi Faculty Award, which is given by, among other institutions, the German Physics Society. They were given this for the development of Firefox and its lasting effect for academic teaching and physics classes at school. Of course, the effect became even more lasting because of the COVID forced lockdown. So many of the experiments that Firefox allows you to do, you can do very easily at home. And it has a long list of experiments which are already built in. And you can use the basic measurements to do many kinds of experiments. You can download the data onto your computer and analyze it later. Another nice accelerometer. Of course, when the mobile phone developers put in an accelerometer in their phone, they didn't want to measure acceleration, or they didn't want to enable you to do experiments using that. What they wanted to do was basically figure out exactly which way the mobile phone was turned so that it could turn the pictures in the right direction and so on. But all those things can be also made dual use. You can actually use the sensors which were meant for other purposes in the mobile phone, can convert that into sensors which actually measures experimental inputs and use them to make your mobile phone perform physics experiments. Now, since I'm talking about sound, there are several acoustic experiments built already into the system. For example, you could just use two phones and a relatively quiet place to measure speed of sound. Or you could use another In fact, you could measure the speed of sound in another method, which is essentially put your mobile phone close to something which can reflect the sound. You send out a sharp note, a chirp. It goes and reflects on the wall, comes back to you. You can measure the time delay. And using that and the distance from the wall, you can measure the speed of sound. There are many other things you can do with this. Many other things. And that would take at least one lecture, if not more, to describe. And more importantly, you can also customize and design your own experiments. So my colleagues at IISER Kolkata, they are actually trying to do this, especially, well, we have been forced to do this because our students also don't have access to the lab now. Hopefully that's going to change in the coming months, but we have at least had kept them engaged and made them do a bit of the labs, at least some hands-on labs, by using Firefox and using very simple equipment which is available in every home. And even, my point is, even after COVID is over, even after lockdown goes away, we started experimenting with Firefox and other things before the lockdown. So this is definitely a resource that is worth exploring, especially for physics teachers and for physics students as well. We should be able to design our own experiments, modify experiments that are available, or simply use the experiments that are already built in and help us to work more effectively now with more modern techniques. Some of the experiments, and these experiments would be way cheaper to do. Everybody has a mobile, nowadays almost everybody has a smartphone. At least in a group of 3 students, definitely there will be two smartphones. In the lab myself, that when a student takes a video himself and then uses Tracker to analyze that, or makes a recording himself or herself and uses that, then it actually gives them a sort of sense of accomplishment which is perhaps not there when they're using some rather heavy, big equipment to record the same thing. So at least we have found that, in a sense, students own these experiments more. Of course, this was before COVID, when we actually could make them do this in the lab themselves. We had an NPTEL workshop where students from all over the country came to our institute and we tried out several experiments. This was one of them. And many students were very enthused about it. In fact, we were rather surprised at the degree of enthusiasm. But they themselves told us that, okay, this is something where everything is being done from scratch by them, using equipment that they own, no fancy lab equipment or anything, and they like the whole idea a lot. So this is something which I would want to request the teachers also to think about, because sometimes using fancy equipment which is available in the lab may detach students from a feeling of ownership. At least I found that many students were more enthused by the fact that they could do everything on their own, rather than how accurate the experiment was or other things. So that's definitely worth exploring, even after the pandemic is, at least, if not over, at least, has lost its sting so much. Okay, so I am done. I have to end, of course, with a thank you to all of you for bearing with me for so long. And I'm open to questions if you have any.
I think there is only one question.
Yeah.
In the chat box. What exactly are we supposed to calculate from Audacity app? Like the time
Audacity
it bounces, or from sound energy we get the lost kinetic energy?
No.
And circulate the electricity of
what you could, of course, measure various different things. You could use, but in this particular experiment, all we are measuring is the timing of the bounces. Now, these times are actually pretty close together. They are less than a second apart. To begin with, they're about a second apart. After a few bounces, they get a fraction of a second apart. So it's very difficult to measure them using a stopwatch. And in fact, measure successive bounces using a stopwatch, using the pause and resume, would be very, very difficult. But here, what we do is record the sound once and for all, and then just simply measure the times of using the screen. So that's what I showed there. Let me just go back to.
Probably she must have joined late.
Yeah, so this is basically what you do. You measure these times. So this first screen shows that you can, this is basically what you get to see when you open the file in Audacity. You get to see the bounces clearly, but then you can, actually it's pretty easy. You can put your cursor, and click somewhere close to this. That ensures that stays at the center of your screen, and then zoom in. Now, as you keep on zooming in, you can zoom in you can zoom in way beyond what I have shown here. But after a while, it becomes difficult. If you zoom in too much, you may not be able to find, this whole thing may actually fill the screen. But using this, you can easily find the moment at which the thing is rising. So that is the moment the ball hit the surface. And you can do it at a very high precision. Here you can see that you can measure it to around a fraction of a millisecond. And as I said, you could write a program using the Python sound library or any other sound library in any other language of your choice to automate the whole process. But here all I did was just visually look at one bounce after another, click at the, so I just unzoomed every time and say I wanted to measure this, I would click on this and then zoom in. Okay, I think I can try showing you Audacity itself. Yes. Okay. So this one, of course, doesn't have any inputs. Now, unfortunately, I don't have the bounce file in this particular thing. So I will just open this is essentially a recording of for a class. So you don't have sharp bounces here. But what you can do in Audacity, for example, is you can amplify the whole thing first so that you can see the thing more. And now suppose I want to find out the exact time at which this thing has happened. This is, of course, maybe for some reason I spoke a bit louder here. So I first click close to it, just so that I won't lose it. Then I zoom in. And as I zoom in, of course, I can see this is the time at which that particular thing happened. If you want the peak, I can put the cursor there and I can keep on zooming in. And I can see this is showing 1.1200. This, of course, will not be sharp sounds like that. This is just human speech, waveforms for that. So this won't be sharp, bouncing, precise sounds like that. But you get the general idea from this. Now, of course, if I just click on this, you can read this particular menu. You should be able to see what kind of things you can do. You can change pitch, you can change speed, you can change tempo, you can remove clicks automatically, you can add in echoes, fade in, fade out and all that. This is, of course, for music editing or sound editing. That's what it's really meant for. Then add reverberations, you can stretch the sound out, and do all kinds of things. But those are things which actually are very nice and nice to learn also, because especially if you're interested in music, or if not, I'm not really great with music myself, but you can definitely use it to edit your own recordings and stuff like that. Freely available and very, very easy to use and very easy to learn. Right now, I was just using it to time. So here I can see this is 1.119, 1 minute 11.95 seconds. This is 1 minute 12.00 seconds. And then I can zoom in further and try to see how precise. This is, of course, being human speech. Is it a particular? You can, of course, measure the wavelength and all that, but you don't even have to do that. Or that's the frequency measurement. You can, of course, you do have a Fourier. You can plot the spectrum of this. So if you select the thing and then, so the other things you can do, for example, one thing I was trying my hand at, if you try filling up a water bottle and just listen to the sound, you will see the wavelength or frequency of the sound keep on going up as the water fills up. That's of course obvious. That's a smaller air column leading to a smaller wavelength, resonant wavelength, and that of course reduces the wavelength, increases the frequency, but also reduces the amplitude because you have smaller amount of air. So you can record that sound, plot its spectrum, try to see from that whether you can. One thing I'm trying, I've not succeeded very well in that yet, so I didn't really talk about that in today's lecture. But one thing I'm trying to do is whether you can actually reconstruct the shape of the bottle, whether it's actually fully cylindrical or whether it has a waist, a widening or something of that kind, from the sound itself, from the spectrum of the sound. You should be able to, but right now I've not had too much success with that. But there are many other things you can do using this kind of thing.
Sir, I have a question. What was the dimension of that steel ball which you have used?
So we were using small ball bearings.
Okay.
Millimeter in radius, I guess.
Okay.
2 millimeters and so.
Okay.
And I also use glass marbles, which are of course bigger, around a centimeter in diameter.
No, but with glass marbles, and then if you are hitting on a glass surface.
Well, glass marbles actually bounce rather well. Then, of course, all this 30 odd oscillation bounces you will not get. You'll get around 10 to 12.
Yes.
Yeah, but even with 10 to 12, you can make a decent measurement. Now, the 10 to 12, actually, that's the point I'm trying to make. If you were to try to measure it directly, those 10 to 12 would actually be very, very faint, the lower ones, and you will not be able to actually measure them out very nicely. But with the recording and amplification, you can easily find out. So once you have the recording, you can actually do a lot of other things. You can get rid of the noise, but here you don't need to. But you can do a lot of other processing to that software, to that thing, and all of that you can do with Audacity. You don't really need any other software for that.
Okay, that's great. Thank you, sir. Thank you. If are there any queries from the participants? Sir, it was too. I mean, you have made it so simple that I think everybody must have understood.
So usually, look, that you understood it, but more often it's because people fell asleep, which is fine, I guess. That's more likely, but still.
But
nice of you to say that this was so easy.
Yes.
Okay.
So if
I'm
there
done.
are questions, shall we?
Nobody has any questions, I guess. So
Yeah.
should be for me, I guess.
I hand over this to Dr. P.K. Samantha, HOD PK College. I definitely would like to thank you, sir, from my personal behalf, as well as DP Khandelwal Birth Centenary Celebration Committee. And I also thank PK Science College and Contai Science Academy for giving us all the technical support, and especially Dr. Pradipta Panchadhyay for coordinating this very well. And so for formal vote of thanks, let me invite Dr. P.K. Samantha, HOD, PK Science College, Contai.
Okay. Thank you, madam. Thank you, madam. So it's a very lucid and nice lectures. In fact, actually, I personally also had attended several lectures of Professor Ananda Dasgupta. So he presents all these things in a very lucid way so that the students can easily do these experiments in home using only a simple mobile phone. Last time he explained about this Audacity software, and last time you also had a lecture from Professor Minaz Hussain, who also explained about the tracker software. I think if the students use all these things and Firefox, etc. So these are quite very huge resource to understand the basic phenomena of physics, basic experiments they can do with all these things in home. It doesn't require any large infrastructures lab. So I hope students have enjoyed all these things, and on behalf of this webinar organizing committee, I must thank Professor Dasgupta for his deliberation, because he has just recovered from COVID and still have managed such a time and encouraging lecture for our students also. So students will be benefited for this, and we are very much thankful to sir. I must thank IAPT for for their association and all the associated members with this P. Khandelwal birthday celebration committee for spreading physics education, this hands-on experiments amongst the students to make physics very enjoyable. I must thank all the supporting staff and all stakeholders of PK College Contai and obviously Contai Science Academy for managing this entire program. I must heartily thank Professor Subhash Samanta for his constant encouragements and being associated with us for doing this kind of activities for spreading this science educations among students, make the science popularized so that the students are motivated to take this physics as their career, obviously. And I must thank the administration of PK College Contai for their permissions and always being with us for organizing such programs. I heartily thanks Madam Professor Rekha Ghorpade for convening today's program. In fact, he is convening the previous programs also. And finally, I would also like to thanks Dr. Pradipta Panchadai from Physics Department, PK College Contai. He is basically coordinating all the entire things. And special thanks to all the participants for which this program has been arranged. And without their participation, it has no meanings. And we'll be very happy that if you do these experiments, if you learn something and if you do some hands-on experiments by learn from this webinar, and we'll be very happy if you feel any kind of problem, any kind of queries, you can directly contact it with us so that we can contact with the speaker, and we shall be very happy to connect with you all so that this physics education we spread amongst the students, so that they get motivated to take physics as their career. So thank you all. Thank you very much for your presence in this webinar. So thank you, ma'am. Over to you.
Thank you, everyone.
Okay, so I'm leaving the meeting now. Is it okay?
Yes, thank you, sir, once again.
Thank you. Thanks all.
Many thanks.
Prabhat, very nice to see you again. But anyway, we can only see each other this way nowadays.
Okay.
Garipto,
We like to
really
Dr. Dasgupta, we like to continue this program in future also, in near future. Okay, I think we shall get always.
Yeah, but you should get experimental, proper experimentalists for that. I am, as I say, just a poor theoretician. I don't really understand experiments that well. Anyway,
whatever lesson that will be fine for our students. Whatever you understand, that will be fine for our students. Okay.
Okay. Anyway, I'm always there. I'm just a bit too busy right now with other stupid stuff, but hopefully that will be short term. Okay, bye then.
Thank you, madam, for
Thank you, sir. Thank you.
Thank you.